There are other examples of linear second-order recurrence relations that are a little bit more applied and useful than this. Let's consider an economic model that involves time delays. This one's really cool. Let's say that we're trying to raise livestock, and we start doing some economics, right? So you got supply, and you got demand, and everything is based on price. Let's call the price P. And let's say that the suppliers are willing to raise a certain amount of livestock, S of P. It's a function of price. Let's say that this is an affine function, so S naught plus A times P. Likewise, the demand for the purchase of livestock is going to be some function of P, some affine function of P, let's say D naught minus B times P. Here, these constants A and B, there's something like price sensitivities. They are going to be positive constants. Why positive constants? Well, the higher the prices, the more the suppliers want to raise them because they're going to get more money. And the higher the prices, the less that people are willing to buy. Hence the positive and negative slopes here. Now, you've had some basic economics. Maybe you know what comes next, right? Supply equals demand. However, here's the interesting thing. This is raising livestock. Let's say that it takes 2 years to bring a product to market. You decide now how many pigs you're going to raise, how many cows you're going to raise. And let's say it takes 2 years to bring that product to market. Now, maybe it doesn't take 2 years to get a market-sized pig. I don't know. But if you're doing something like semiconductor manufacturing, where it might take 2 years or more to build a plant, get the assembly lines up and running, get the product out, this sort of time delay, this is where it gets interesting. Because now your price variable is a discrete time variable. Now, what do I mean by that? Let's write out a model where supply and demand are set equal to one another. So supply, S naught plus A times P, equals demand, D naught minus B times P. But now we have Pn, or more precisely, we have Pn on the supply side and Pn plus 2 on the demand side. Let's pause for a second and think about why. The number of hogs or cows that I decide to raise is a function of the price right now. The demand for those products is a function of the price 2 years from now when it's ready to come to market. This is giving us a linear second-order recurrence relation. If I move things over to the left-hand side, then what do I get? I get Pn plus 2 plus A divided by B times Pn is equal to D naught minus S naught over B. Now, this is not quite the model that we have been working with. This is not autonomous. This is what we would call an affine recurrence relation. Now, we do have a nice linear part. We need to modify things just a little bit. And here's the idea. We can move from an affine system to a nice linear system via a simple change of coordinates. Let's define P star to be equal to quantity D naught minus S naught, all divided by A plus B. That is really the price equilibrium, and it is indeed an equilibrium of this affine recurrence relation. And I'm going to do a change of coordinates. I'm going to let Q be equal to P minus P star, the deviation from this equilibrium price. Now, what happens when I substitute that into our affine recurrence relation Pn plus 2 plus A over B Pn equals D naught minus S naught over B is I say, look, Pn is really Qn plus P star. Pn plus 2 is really Qn plus 2 plus P star. I do that substitution. What you get is Qn plus 2 plus A over B Qn equals 0. Now, it takes a little bit of work to show. You can do the algebra on that. What I want you to do is look at this. What does this look like? That A over B, that's a positive number. This looks a little bit like a discrete time simple harmonic oscillator. Indeed, if we write down the characteristic equation for this linear recurrence relation on Q, we get lambda squared plus A over B equals 0. That means that our roots, lambda 1 and lambda 2, are plus or minus I times square root of A over B. They are pure imaginary. Now, remember, this is discrete time, not continuous time. So what really matters is the modulus, or the magnitude of these complex conjugate eigenvalues. If I rewrite this in polar form, lambda is going to be square root of A over B times e to the plus or minus I times pi over 2. Then that modulus is root A over B, and that argument theta is pi over 2. Then we have the general solution. Given this presentation for lambda in terms of its modulus, its argument, we can write Qn equals C1 times quantity A over B to the 1/2 to the nth power times cosine of n pi over 2 plus C2 times quantity A over B to the 1/2 to the nth power times sine of n pi over 2. Now again, this Qn is almost what we want. It's Pn minus P star, the deviation from the equilibrium price. And what we see is, with all these cosines, with all these sines, that this sort of oscillates by jumps, kind of like a discrete time simple harmonic oscillator. But what really matters is that A over B quantity that we're taking more and more powers of. Because depending on the ratio of A and B, this can get really wild. In fact, we're going to have unstable dynamics if A is bigger than B, because that number is bigger than 1, and so we're just getting higher and higher powers. On the other hand, if A is less than B, and remember they're both positive, then as n increases, this is getting smaller and smaller and smaller, so that we're converging to this equilibrium. Everything depends on this price sensitivity ratio. All right, that's the solution, but what does it mean? What it means is bound up in the eigenvalue, in lambda. Looking at these eigenvalues, lambda is plus or minus square root of A over B times I. The first thing is, because it's pure imaginary, it implies that there is a 4-year cycle. You're taking powers of this, and we know how powers of I behave. And that 4-year cycle means that there's a sort of a supply-demand price shock that's going on, where first there's oversupply, and then the price collapses, and then because the price collapses, suppliers are willing to bring more to market, but then it takes time, and then by the time it comes back, you get this 4-year cycle. Now, this sort of time-delayed dynamics leading to instability is something that you see elsewhere. Maybe, I don't know, maybe you've been in a shower that has sort of a hot-cold control, and you get in the shower and the water's too cold. And so what you do is you turn the dial to make it hotter, but it takes a while for the hot water to come in from the tank up through the pipes, and then by the time it gets to you, oh my God, it's too hot. So you're like, oh, turn that thing back down. And then, whoa, it's too cold. And then depending on the ratio of sensitivities and the magnitude of the time delay, you can get either stable or unstable dynamics where it gets worse and worse instead of better and better. What we've seen in this model is an economic version of that. TLDR, everything depends on the eigenvalues.